Hello, my name is Jae-Young from IIIE Excel Lab. Today I will be presenting a paper, LGTM, Local to Global Text-Driven Human Motion Diffusion Model, which was published at SIGGRAPH 2024. Text-to-motion generation is the task of generating 3D human motions based on natural language descriptions. For example, given a description like a person is running on a treadmill, the model generates a motion sequence that aligns with the input text. In previous approaches, motion generation was primarily achieved using diffusion models, which take modalities such as text as input conditions to produce high-quality results. Previous text-to-motion generation methods face two key challenges. First, they struggle to capture subtle contextual nuances in text descriptions. For example, in "a person drinks hot coffee," current models fail to reflect cautious movements required for handling something hot. Second, they lack local semantic accuracy for body parts. In "a person draws a circle with their left hand and a square with their right hand," the model often generates incorrect or mixed motions, failing to differentiate tasks for each hand. These limitations highlight the need for better local precision and semantic alignment to create realistic motions. To address the challenges we discussed earlier, this paper introduces a novel approach called the local to global pipeline. This pipeline is designed to simultaneously achieve local accuracy and global coherence. Local accuracy ensures that each body part performs the actions described in the text with precision. For example, in the text, if the text specifies that the right hand waves, the model ensures only the right hand performs that action. Global coherence guarantees smooth and natural interactions between all body parts, resulting in coordinated and realistic full body motions. And this is the overview of the proposed method in this paper. It consists of three main components: the partition module and the part motion encoders and the full body motion optimizer. Firstly, let's discuss the partition module, the first component of the LGTM framework. The partition module is responsible for decomposing the input text and motion data into smaller body part specific segments. This process is essential for augmenting the data and ensuring precise alignment between text and motion at the local level. All input data is divided into 6 body parts: head, torso, arms, and legs. Now, let's take a closer look at how the partition module processes text data. For text data, the partition module uses a large language model to decompose the global text description into detailed instructions for each body part. The LLM automatically maps the input text to specific actions that each body part should perform. This decomposition ensures that each body part receives clear task-specific instructions, setting the stage for precise motion generation in the next stages of the pipeline. Secondly, let's discuss the part motion encoders, the second component of the LGTM pipeline. The part motion encoders independently process text and motion data for each body part encoding them into embedding vectors. This ensures that each body part is treated individually while maintaining precise alignment with the text. The encoders take three inputs: part motions, part text, and the diffusion time step. By processing these inputs, the encoders generate embedding vectors for each body part. And the part motion encoders use two key components to process motion-related text and sequential data effectively. First, the TMR encoder is employed as the text encoder. Unlike general-purpose encoders, it is specifically trained to encode motion-related text, allowing it to capture fine-grained semantic details needed for precise motion generation. Second, the conformer block replaces the traditional transformer encoder block. This block combines convolution and transformer layers, enabling it to run both the temporal and spatial features of sequential motion data more effectively. The combination ensures accurate representation of both short-term and long-term dependencies in motion sequences. As a result, the part motion encoders produce embedding vectors that represent the motion for each body part with high accuracy and semantic alignment. And lastly, let's explore that full body motion optimizer, the final component of the LGTM pipeline. Since the part motion encoder generates motions for each body part independently, a process is needed to understand and synchronize the relationships between body parts. The full body motion optimizer addresses this by using a notation mechanism to ensure smooth coordination and natural interactions between all body parts. This step is essential for creating realistic full body motions that align with the input text while maintaining both temporal and spatial coherence. Without this optimization, the independently generated motions might appear disconnected and unnatural. The full body motion optimizer works by combining all the embedding vectors for individual body parts into a single vector that represents the entire body. This full body vector is then combined with the text embedding vector of the input text to create a semantically aligned motion representation. After passing through the attention encoder, the model generates an optimized embedding vector that reflects the relationships between body parts. Finally, smoothness is applied to refine the motion and eliminate artifacts such as jitter, producing clean, realistic motion output. This process ensures that the generated motions are smooth, natural, and fully aligned with the input text. And this paper uses a dataset Human ML3D for evaluation. This dataset consists of around 40,000 motion sequences paired with 44,000 text descriptions. To evaluate the performance of LGTM, various metrics were used. First, metrics like FID, diversity, or precision, and multimodal distance measure overall motion quality, diversity, semantic alignment, and cross-modal consistency. However, the focus here is on the part-level multimodal similarity metric. This metric assesses how well individual body parts motions align with the text descriptions. So LGTM achieves the best performance across multiple metrics and also achieves better alignment with text in both global and local semantics, as evidenced by its superior PMM similarity scores for all body parts. These results demonstrate that LGTM's superiority over previous methods. And this is a qualitative comparison result of this paper. These results highlight the LGTM's ability to outperform existing models in generating precise and realistic motions. This is the end of content. Thank you for listening.